Gauge RNR study or measurement system analysis or measurement system capability analysis. They're known in so many different names. We'll be discussing about the Anova method using the Microsoft Excel. We'll have to use Microsoft Excel. So this is a typical scenario for a gauge RNR study data. So you have 20 different parts measured by 3 different operators, and then each of the part measured by each operator 3 times. So this is a typical scenario of a gauge RNR study data. And then to use Excel, Excel doesn't have I don't know there is a direct analysis function that we can use to directly perform the RNR study, but it will take a little bit of couple of steps to finally do the analysis. Mostly manual, but most of the complex calculation will be done using some Excel function. So first, because it's an Anova method, we'll have to run the analysis of variance or Anova, and Excel only takes data on this format to perform the analysis of variance first, and then we'll use those data to get all the gauge RNR parameters and see whether our gauge is capable or not. So basically, here is the data file, and then I convert it to this format. So these are the part numbers and then the operator, and this is the replication for each part for each operator. So first we have to analyze the analysis of variance, perform that. So under data, you can click on the data analysis tool pack and select 2-factor Anova. We have 2-factor, one is part number, and then the other one is the operators. And also we have replication. 3 replications were made for each part by each operator. So hit OK and basically select this data, and then you probably have 0 there, so select 3 replication per row. So then just hit OK. It will produce this long list of stuff. But what we need for gauge RNR study is this Anova table. Everything else for now we really don't need it, so I'll basically delete it. So I have a clean Excel file like this and make it a little bit larger. Like that. We also do not need some stuff like none of this is needed for this analysis. So sample here is the operator. Basically Excel has some kind of weird way of naming all this stuff. It is the operator, and then these columns are part to part variation or process variation. We'll simply write process. And then the interaction is operator times process. And the within variation, that is the repeatability. So I'm going to add one maybe. So we can do the process will move up right there. I will move down this. So this is our reproducibility. Can the operator reproduce the measurement? Reproducibility. I hope I spelled that correctly. So these two are related to the operator efficiency. How capable are these operators to measure this stuff? So we can simply sum these two to get it here, but let's calculate those. The first we're going to calculate some parameter based on which we'll say whether this system is capable or not. To do that, we need these formulas. So I'm going to copy them down. To find these formulas, you can go to the openeducator.com under statistical quality. You can download all these equations. I'm going to copy here just for my reference, so I can see it when I write this formula. Copy this one, so that goes there, and then one more. We don't need to copy the last one, the experimental error. one like this. So we'll type here variance. So variance for the process, which is the P or part-to-part variation, equal to MSP, this guy, minus MSPO, which is this, divide by the number of operator has 3, and then divide by the replication, which is also 3. For the sake of understanding, I'll write here P, this is O, and then I'll write this P times O. I think that should be enough. All right, so this one for the operator part, so this is the formula for that. So parentheses MSO, which is this one, minus interaction divided by the P part number, which is we get 20 part or process, divided by 3. Then this one would be equal to the interaction one, so we're going to use a parenthesis, the interaction, so this is the formula, interaction minus the MSE, which is this one, close the parenthesis, divide by N, which is 3. So now we can calculate the percent variation due to these different factors. So this is basically simply the experimental error, and the total we can simply sum this, all of this like this. So that's the total. I think I should sum it in a different way. This, and this. So that is equal to the percent variation due to the process is this divided by the total, which is this, and then I'll freeze that because I'm going to use it for all the rows times 100. So then I can simply copy that all the way down here. Nothing exists here. Too many decimal points. I really don't need that many. It should be good enough. Like that. Okay, so now we got the percent variation. So you can see that the process variation is about 93%. Rest is the about 7% is due to the gauge. So all of these are related to the gauge. So we can maybe, I don't need this formula anymore. So I can write here something like gauge total which is the sum of this, and this. And then the process total, which is this guy. And that should be 100% because we distributed the whole thing to 100% like that. Now let's calculate the precision to tolerance ratio. So with respect to the variance component, the gauge is contributing about 7% variation in this measurement system. So which is okay, not too bad. But what determines whether a system is capable or not is this precision to tolerance ratio, which is the 6 sigma divided by the control limit. So the spec limit. So let me have that. Let's say we have 65 upper limit and then 5 lower limit. So the range is 60. So that is equal to 6 sigma. So 6 times sigma, which is sigma is the square root of the variance. So SQRT of this piece divide by this guy. And I will freeze that because I'm going to use it for all the following rows. We can make it in percentage, so times 100%, maybe, and then I can simply copy this here. So that is the precision to tolerance ratio percentage. So as you can see that the total repeatability is not really, so it has to be under 10%. So PT ratio less than 10% is considered good. 10% is indicate an adequate measurement system. Now, as you can see here, the process variation is about 67%. So if we calculate the total here, I can simply expand this to this guy here and this guy here. So that's the PT total, which is about 29%, which indicate that this measurement system is not capable. That's percent variation. So if it's less than 10%, then it's okay. If it goes over 10%, then it's not okay. It's not a good measurement system. I'll put it here and then just like this so that it looks cleaner. So just to summarize how to perform this analysis using Microsoft Excel, you have to have the data in this format and then run the analysis of variance from the data tab, going to data analysis and then two-factor ANOVA with replication. Once you get that, then the result will come in, produce this ANOVA table, and after you get this ANOVA table, calculate the variance, percent variance, and precision to tolerance ratio, and decide based on this piece whether it's a capable measurement system or not.